So I want to introduce these two wonderful, hardworking researchers um, before they get started because they have done a fabulous job not only in doing their own research, but teaching other groups how to use quantum computing, teaching other groups machine learning in general, and submitting their stuff outside of ASDRP and JEI. I think they have done a fabulous job in their time here, and I will turn their presentation over to them. Thank you very much, ladies. Oh, by
Thank
the
you.
way, and you didn't put my lab
Oh, yeah, I'll add.
logo thingy on the slides.
Yeah, I'll update that.
All right, go ahead, go for it.
Okay. Hi, everyone. As you know, we're from Dr. McMahon's lab, and we're doing research on using quantum neural networks, quantum vision transformers, and the mathematical morphological reconstruction algorithm for brain tumor detection. I'm Tiffany Liu.
And I'm Riddhi Sharma.
So for a quick introduction, brain tumors are the uncontrollable growth of cells that form a abnormal mass of tissue appearing in the glioma, meningioma, and pituitary areas of the brain, and they can be either benign, being non-cancerous, or malignant, being cancerous. They also come along with a lot of symptoms, including fluid blocks, brain pressure, internal bleeding, and loss of balance, vision, and memory. The rising rate of undiagnosed and inaccurate brain tumors is affected by current approaches, which cannot detect the formation of these tissues early. In fact, the National Brain Tumor Society states that 1 million Americans live with a brain tumor, where 94,390 people get a diagnosis, which includes a 35.7% relative survival rate in 2019 alone. So our team is essentially approaching this inefficiency by investigating different algorithms, including the mathematical morphological reconstruction algorithm, quantum convolutional neural networks, and the quantum vision transformers to result in an early stage detection model with skimage, TensorFlow, OpenCV2, and Qiskit. So currently, the most common form of tumor detection is done manually by radiologists with MRI scans or magnetic resonance imaging. So this clearly poses a few issues. As the amount of data has been rapidly increasing, it's become a lot more inefficient and tedious to manually sort through all of this data. Further, this form of detection relies heavily on the experience of the radiologist, which may be prone to error. And also, a lot of areas don't have access to the resources or doctors necessary for this kind of detection. So in an attempt to address these issues while also accounting for accuracy and speed, there have been a lot of recent and successful developments in deep learning approaches, specifically with CNN algorithms. And that leads to the basis of our research to see if the MMR, QCNN, and the QVT algorithms would perform better, and essentially see if introducing this quantum aspect could give us any advantage.
So first we start by collecting a data set of 2,000 tumors and about 2,000 non-tumorous MRI images, which is then split into an 80-20 training to testing ratio, built with various tumor shapes, types, and orientations. To start up the process, the images go through pre-processing, which is done in the skull stripping algorithm to isolate the brain, and the output of the skull stripping acts as the input for all of our algorithms. Our main goal is to extract the best features of the models to make a final model that increases the diversity for different kinds of tumors, since the MMR's principle is based on the analysis of shape and structure. In contrast, the QCNN and QVT algorithms are based on classification to recognize patterns in more complex data. So our first step to our model is skull stripping, and skull stripping is one of the many pre-processing steps that we're going to include. But for now, skull stripping is a vital pre-processing step when analyzing brain MRIs for any purpose, including tumor segmentation. And in MRIs, the skull and the intracranial tissues, which aren't part of the brain, have the same bright intensity as the brain and its tissues, so it makes it harder to segment the brain if you don't first isolate it from the skull. Also, the parts that don't belong in the brain add a lot of unnecessary noise and detail. So the overview of the skull stripping process is that it goes to binarization through adaptive Gaussian thresholding. Then the two images are created to overlay on top of each other for contouring. Then there's a process of mask and marker creation. And once we overlay the mask and the marker, the contouring is created. And that means the contouring is going to plot the outlines of the segmented image. And until we get a good middle ground, which means until we have enough edges and gaps, we can maintain the original picture's general contour with a good level of detail and not too much noise. And finally, we will get the remaining part of the overlay, which is the brain, which is segmented out. So as you can see, these are some results from the skull stripping. The top layer shows the original raw data with the skull. As you can see, it's of bright intensity, and the model might get confused since the tumor is also of that same bright gray intensity. But now that we removed it, more of the model's focus is going to go towards the tumor. Okay, sorry. So the next step in our algorithm is the MMR, the mathematical morphological reconstruction, and we've gotten results for the MMR. It's a 92% accuracy rate. So MMR enhances and extracts image structures by iteratively combining dilation, erosion, and watershed thresholding operations throughout its iterative process. Dilation enlarges regions in an image, whereas erosion erodes the boundaries of regions in an image. And the algorithm removes noise and artifacts by creating the marker image, which represents key points, and a mask image, which is derived from the region of interest, and morphology operations for noise removal. Finally, watershed thresholding and segmentation is applied, and based on the concept of segmenting the region of interest through a watershed line. So the creation of the marker and mask images guides us to the 4-step reconstruction process. After fine-tuning noise removal with a peak signal-to-noise rate of 39.8, subsequent morphology operations are then deployed. The integration of watershed thresholding and segmentation leads for us to have a 92% accuracy stage rate for early-stage tumor detection. And as you can see, these are some detection results from the MMR algorithm. The tumor is circled in red in the raw image, then it's skull strip, and finally, that's the output we get from the MMR algorithm. And we plan to add this algorithm
I'm just going to
to our
dial in
model.
myself.
We plan to add this algorithm to our model because of tumor diversity in our data set, as the MMR is a less strong algorithm compared to the other two quantum algorithms. It doesn't have to go to expensive computation, and we will use scans with more vibrant tumor gray ranges for this model.
Okay, our next algorithm is the Quantum Convolutional Neural Network, or the QNN. So at this stage in our research, we're currently training the QNN and we'll complete testing to get results soon. So to give some background, we'll be applying the architecture of a classical convolutional neural network in a quantum environment. So the CNN is a deep learning algorithm that feeds training data and detects patterns to process and classify our dataset. And a classical CNN will consist of an input, some hidden layers, and an output layer. So for example, here there are 2 hidden layers, but you can customize these towards your goal. In this image, these circles are perceptrons, which just take an input and then they give an output. And the algorithm sorting process adjusts these weights to detect different patterns. So to take a closer look at these hidden layers, in our case, we're primarily looking at convolutional and pooling layers. The convolutional layer performs feature extractions, and then the pooling layer reduces the dimensionality of the MRI scan, and finally, the output classifies the scan. So our QCNN will use classical data with quantum computing, meaning our quantum convolutional neural network will have a combination of quantum computing concepts with the classical CNN that we just discussed. So like the classical CNN, we'll also have convolutional and pooling layers, but instead of using this classical data, we'll be using qubits and quantum circuits. As you can see in this image, we plan to apply alternating convolutional and pooling layers, and that's going to be applied on the quantum circuit. The secondary purpose of our research is to test if the QCNN has a better accuracy or speed than the classical CNN. So the QCNN algorithm contains 3 main parts: the encoding, processing, and measuring of the data. First, the encoding consists of the classical input data, so the brain MRI scan, being converted to a quantum circuit through angle encoding, which just puts qubits into superposition for parallel computation and applying rotations so that the data can be further processed. Next is the processing step. So similar to the CNN's hidden convolutional and pooling layers, we're going to be applying gates and entanglement with specific parameters. So the convolutional layer would involve the same feature extractions like the CNN we just discussed, and the pooling layer would also reduce the dimensionalities, but in this case of the quantum circuit instead of the classical data. To do this, we encode the information from one qubit to the other qubit, and once we do that, we can disregard the original qubit for the rest of the process. So as you can see in this image here, the data from Q0 is encoded into Q2, and then the data from Q1 is encoded into Q3. So at the end of this pooling layer, we can just disregard Q0 and Q1, and we're left with Q2 and Q3. So this pooling layer would allow us to reduce the number of qubits in our circuit about half, in this case from 4 qubits to 2 qubits. And we would continue to repeat this until we're left with 1 qubit, serving its purpose of a smaller representation of the data without removing important information. And then lastly, we would measure the output of a single qubit through a softmax layer, which forms the probability of a specific state, which is then translated to what that means classically. So it tells you whether or not there is a brain tumor.
So the last part of our model is the QVT, the quantum vision transformers, and right now we're working on training and testing. So before we delve into the quantum aspect of the QVT, let's analyze the classical model first. So vision transformers are an image processing-based neural network architecture that has recently grown quickly by combining powerful techniques such as self-attention, which means allowing each element to make relationships with other elements through the comparison of the significances of each feature for spatial information. And the purpose of the QVT in our model is to overcome the challenges of the QCNN, such as capturing global relationships, increased scalability, positional embedding, and being restricted by a certain number of layers. And we can go through the vision transformers process by referring to this image. Firstly, the vectors are extracted from the image and then split into 16 by 16 patches. These patches then get embedded through linear projection. So the purpose of these patch embeddings is for parallel computation and for retaining positional data, which will be then processed by an encoder. The vision transformer encoder contains two main layers, the multi-self attention layer and the MLP head. And before and after these layers are normalization and feed-forward layers, respectively. The purposes of these multiple layers is to make residual connections, to prevent overfitting or generalizing new data, and to prevent data loss. Before analyzing the multi-self-attention layer, we need to know exactly what self-attention is. So self-attention is a mechanism typically used in neural networks that allows a model to weigh in all the parts of the input image, not just localized regions like the CNN. And this means that the vision transformer will compare every pixel with respect to every other pixel in the input. And the importance of these inputs are stated as attention scores. And technically speaking, the concept is represented in the encoder through three key parameters, carry, key, and value. And these parameters calculate the attention score. And respectively, they compute, compare, and represent each image in each element in the sequence. The model splits the parameters n ways and passes them into the attention head. Through the linear layer, these parameters contribute to the score by calculations with the information of positional embeddings earlier found in the linear projection. And at the end of the cycle, information from the three parameters go into a single matrix for an attention score as the output. And after going through the normalization and feed-forward layers, the data then gets processed into the multi-layer perceptron head to introduce non-linearity to refine relationships within our really complex data. The attention score goes through a series of linear transformation and nonlinear activation through a ReLU activation function, and the transformed attention score goes through the masked self-attention layer, or the decoder, where the model is trained to differ from the masked patches versus the normal to prevent overfitting. And then this transformed score goes to the classification head to get the result if a tumor is present in the image or not. And now that we understand the classical aspect of a vision transformer, let's delve into what quantum can contribute to the VT. So for the QVT, we're adapting a shallow quantum circuit, which is a quantum circuit with minimal depth, which can be used in the multi-self-attention and MLP head layer in the encoder. Specifically, we will be focusing on the data loading methods, such as a quantum feature map and compound matrices, and both of these provide an advantage of runtime and the number of model parameters that can be used. But aside from data loading, we would be adapting quantum orthogonal layers, which replaces the MLP layer for quantum applied nonlinearity instead of normal nonlinearity. And in the first image, the patches are loaded into the qubit with the states, and then it's processed to the quantum orthogonal layer with additional variations of the data at, for example, its inverse to prevent overfitting. And this layer creates a probability state, which helps preserve the circuit data through matrix computation.
Really, that costs 99 a pound. So I got 1 pound.
It's good.
Mm.
It's cheap.
So finally, our future work includes completing the training and testing for the QNN and QVT algorithms so that we can compare these results to the classical CNN algorithm and the MMR algorithm to see if there's any noticeable advantage in terms of speed or accuracy. And then finally, future possibilities to expand this even further down the line will be to classify types of brain tumors rather than simply detecting them. And this could really help with affecting the action speed for doctors to essentially initiate effective instruction at an early stage since they are able to classify types of brain tumors. Finally, we would like to make a few acknowledgements. First, we'd like to thank our advisor, Dr. McMahon, who's guided us throughout this entire research. We'd also like to thank ASDRP for giving us the opportunity to conduct this amazing research. And then next, we want to thank Adelina. She was a researcher from another group, and she really helped us introduce the quantum computing aspect of our research and sort of set our basis. And then finally, of course, the rest of the researchers on our team who have contributed throughout this research. Here's our sources. Thank you. Anyone have questions?